So to understand this, we can use right hand rule that we used to define the vector product previously. Here, draw the vectors v and b with their tails together. Imagine turning v until it points in the direction of b, and wrap the fingers of your right hand around the line perpendicular to plane of v and b, so that they curl around with the sense of rotation from V to B, and the thumb points in the direction of a force on a positive charge. So the force on a charge Q moving with velocity V in a magnetic field is given by F is equal to Q V cross V, magnetic force on a moving charge particle. And there are several vector products which we are going to study in magnetism, but this is the first one. And this equation is valid for both type of charges, positive and negative. When charge is negative, the direction of the force is opposite to that of this V cross B. If two charges with equal and opposite signs move in the same magnetic field with the same velocity, then the forces have equal magnitude and opposite directions. So this equation gives the magnitude of the magnetic force in a different but equivalent way. Let's suppose we have the angle phi between V and B. So we can interpret this as B sine phi as the component of B perpendicular to V. So this becomes B perpendicular. So with this notation, we can modify this equation V B perpendicular. And this form is sometimes convenient, especially in problem solving involve currents rather than individual particles. Now, the units of magnetic field is must be the same as the units of F over QV. So the unit of B is 1 Newton second Coulomb meter, or it could be 1 Newton ampere meter. This unit is also called Tesla, and it was given in an honor of Nikola Tesla, the prominent Serbian American scientist and inventor. So 1 Tesla equal to 1 is equal to 1 Newton ampere meter. And other unit of magnetic field which is widely used is Gauss, and 1 Gauss is equal to 10 raised to power minus 4 Tesla. Instruments mostly used for measuring magnetic fields are also called as Gauss meters, and the magnetic field of the Earth is of the order of 10 raised to power minus 4 Tesla, or 1 Gauss. Magnetic fields of the order of 10 Tesla occur in the interior of atoms and are important in the analysis of atomic spectra. The largest steady magnetic field that we would be able to produce in the laboratory is around 45 Tesla. So some pulsed current electromagnets can produce field of the order of 120 Tesla for short time intervals of the order of millisecond. And it's believed that the magnetic field at the surface of a neutron star is of the order of 10 raised to power 8 Tesla. So now let's see how we would be able to measure magnetic fields with test charges. To explore an unknown magnetic field, we can measure the magnitude and direction of the force on a moving test charge from here by using this formulation. Let's suppose the electron beam in a cathode ray tube, such as that mostly CRT is used in television, and is a convenient device for such type of measurements. So the electron gun in CRT shoots out a narrow beam of electron at a known speed. If there is no force to deflect the beam, it strikes the screen, the center of the screen. If the magnetic field is present, then the electron beam is deflected. But if the beam is parallel or anti-parallel to the field, then phi is 0 or pi 180 degree, and force is 0. There is no force and hence no deflection, like in this case. If we find that the electron beam is not deflected when its direction is parallel to a certain axis, then the vector, the magnetic field vector, must point either up or down along that axis. Now if now let's consider this case. If we turn the tube to 90 degree, now the angle is phi is pi by 2, 90 degree, and the magnitude, the magnetic force is maximum in this case because the beam is deflected in a direction perpendicular to the plane of B and V. The direction and magnitude of the deflection determine the direction of the magnetic field, and the electron has a negative charge. If the electron has a negative charge, then the force is opposite in direction to the force on a positive charge. Must remember this. So when a charged particles move through a region of space where both electric and magnetic fields are present, both fields exert forces on the particle, and the total force is the vector sum of both forces, Fe and electrostatic force and Fb on the total forces Q E plus V cross B. So let's do some numerical problems regarding these magnetic forces on moving charges. And if you find any problem or in understanding of this basic concept, we will discuss it tomorrow.